This is Edexcel Further Pure 1, Numerical Methods 2, Simpson's Rule. It may help if you have some familiarity with the trapezium rule from A-level maths, but this isn't required to follow this video. Numerical integration allows us to estimate the area underneath a curve where we can't do that by normal means. What we end up doing is subdividing the area underneath a curve into multiple strips, and then using some technique to estimate the area for each individual strip. One method of approximating the function is to use quadratic curves, but quadratic curves need 3 points to fit them. So 3 points means I'm going to need 2 strips for each quadratic curve. So what that means is to use quadratic curve fitting, which is Simpson's rule, we end up needing 2n intervals, an even number of intervals. It can be shown that the area underneath a quadratic curve passing through 3 specific points is given by this formula here. And I've put all the working on this slide, and you can freeze the video if you want to go through it, but the key element is that the area underneath a quadratic curve between 3 consecutive points is given by this formula. If we just use 3 points on a curve, 2 intervals, and we fit a quadratic to go through those 3 points, it can be that we've got quite a large discrepancy. So if we increase that to 4 intervals, you can see we've got quite a tight fit on the first curve, and again quite a tight fit on the second curve, fitting it to our given function. We go another step further, and given the thickness of the green line here, the orange line is on it, the blue line is on it, and the purple line is on it. So that's giving us a very accurate representation. Here are those 3 graphs again, but placed underneath each is the sum of the quadratics that we're fitting to our given curve. And if we start looking at those in more detail, you can end up seeing that we've got a common factor of h over 3. We've got 4 times the odd ordinates. We've got repeated even ordinates, except for the last ordinate and the first ordinate. If we add all those quadratic curve areas together, we still have that common factor of h over 3. We have our 2 end ordinates. We have 2 times our remaining even ordinates, and we have 4 times the odd ordinates. Critical thing with Simpson's rule is that you need to make sure you have an even number of intervals. To make sure you've got an even number of intervals, you can divide by 2n, and you're dividing the overall width between A and B by 2n. Here's a typical example. We're asked to use Simpson's rule on this function, and we're asked to do it to 2 decimal places, and we can use Simpson's rule because it's got 6 intervals. Here is the solution laid out. I'm told to use 6 strips in the interval between 1 and 4, so I've got an overall width of 3. Dividing by 6 gives me a strip width or interval of 0.5. So I've then generated all the x values I need to then use the function y equals e to the root of x to generate my y values, and I've recorded them to an accuracy of 3 decimal places to make sure I don't lose accuracy, because I need to do it to 2 decimal places. Here's my formula: a third of h times the end ordinates plus 4 times the odds plus 2 times the remaining evens. So here are my end ordinates, my odd ordinates, and the remaining even ordinates, and then putting that into a calculator, adding up and recording to 2 decimal places give me 14.78. That was Edexcel Further Pure 1, Numerical Methods 2, Simpson's Rule, and is the only video in Numerical Methods 2.